Alright, in this video we're going to find the global min of this function, which by the way we've got a contour plot here, on the constraint x plus 1 half y equals 1. Now let's just talk a little bit about what we mean by the global min on the constraint. Obviously what we have here is a bowl-like function, and its absolute lowest point is at the origin. But we're asking that x plus 1 half y equals 1. So we're actually looking at the line that connects, let's say, to here, and goes through 1 on the x-axis. We want to know where the function x squared plus 2y squared has its lowest value on this line. Let's think a little bit about what's going on. Clearly, as we go in this direction, the function is increasing, and definitely as we go in this direction, the function is increasing. So we're really talking about someplace right about here. That appears to be where we have the minimum value of the function. So note, and we'll emphasize this again in class, this is where the line appears to be tangent to the contour line. So we can think of the gradient of our function pointing in this direction. Ooh, I wanted that to be perpendicular, but it's close. And the contour of the constraint function pointing the same way. In particular, if we say that g of x comma y is x plus 1 half y, the equation we'll be using on a regular basis for constrained optimization is the following. The grad of f at x comma y is going to be parallel and thus equal to lambda times the grad of g at x comma y. We will motivate this in class, but for right now let's use this equation to see how it works. So grad f is going to be 2xi plus 4yj, that's supposed to be equal to lambda, times the gradient of our constraint function, which is I plus 1 half j. Okay, so reading off i's and j's, we've got a couple of equations here. 2x equals lambda, and 4y equals 1 half lambda. We've also got one more equation, and that's that x plus 1 half y equals 1. So we need to solve these three equations for x and y. Now you can do this in Maple. Since I don't want to pull up Maple in this video, I'll do it by hand. But there are all sorts of different ways you can do this. I will start by solving for x and y. X equals lambda divided by 2. Y equals lambda divided by 8. Plug both of those into this equation. Lambda over 2 plus lambda over 16 is equal to 1. That means that 9 lambda over 16 equals 1. So lambda equals 16 ninths. So x, which is lambda over 2, will be 8 ninths. And y, which is lambda divided by 8, will be 2 ninths. Note that this makes perfect sense. Because if we think about where that point is, yeah, that's not bad for saying we're over 8 ninths and we're up 2 ninths. Notice that this technique really finds local mins and local maxes, but we can tell from the shape of the function as shown on the contour plot that that's actually going to be a global min, that that's our lowest point, and that we will have no highest point. So, to review, this is the equation we're going to use again and again when we want to find the max or min of something subject to a constraint. We'll solve it, we'll find a bunch of equations, including our constraint equation, that'll give us enough equations to solve for our unknowns, and then we'll find x and y. Usually you will want to use either a plot 3D or a contour plot to justify that what you found is a global max or global min.